Okay, here we go. These are the surface area examples I promised to get to you guys. Some additional questions regarding this formula. And here's what you guys always want to remember, is your surface area is 2 pi r ds. The first thing you have to do is determine what your radius is. It's right here, the r value. So for every one of these examples, we're going to determine the radius. And after that, after you know the radius, then you can find whether this is a dx or dy for your ds term. So let's take a look here. Let's look at some more examples. You got y equals the square root 1 plus 4x, where x is between 1 and 5. And we're going to revolve these here. This is going to be revolved about the x-axis. So we revolve about the x-axis. Okay? So we're going to come out to our graphing program, and we're going to take a look at this curve just to show you y equals 1 plus 4x. Okay. And I'm going to change this color. Let's go to blue. How's that? Okay. So we're going to look at this curve from 1 to 5. So maybe something like this. Okay, and let's figure this out again. I guess we have to, yeah. Okay, device, more. Take a screenshot of this if we want to write on this. Okay. So we're going to revolve about the x-axis. Remember, this is going from 1 to 5. So 5 may be somewhere here in the middle between 4 and 6. So we got, looks like it's 1, 2, 3, 4. So maybe somewhere in the middle here. Okay. Here's what 5 would be. 5 would be here. So we're going to take this portion from 1 to 5. Okay. So 1 is over here. And we're going to take this portion here. And we're going to rotate this portion here about the x-axis. Okay? Now, when you rotate this about the x-axis, I want to point out to you that what you need here is a radius value. So this will create a circle of some sorts. I know that's not very good, but I want to point to you, or imply here from 1 to 5, your radius now is going to be something like this. If we can get this to right. Okay. Here's the r value. Here's going to be your radius here, because you're going to rotate this, about the x-axis. And so the curve is going to have some, if I do this a little better. So here's my point. Here's where your radius would be. So if I ask you, how do we measure that particular radius here? Okay, is this an x value or is it a y value? Focus on this. For this particular radius value, this is the same length as what you'd see here. Maybe a little taller, right? So this is that radius value in blue, same value here. So in this case, r is going to be the y value. So for particular value of x out here, your radius is going to be the y value. Okay. So I want to notate this because surface area is 2 pi r ds, and we found that radius to be y. Now that we know to use the y variable there, here's what I would remark to you. The question now becomes, what is ds? Now, you might think ds will be the term that ends in dy, right? But it's not, because if you go back up here, we know how can we represent that y? We can represent y with the square root of 1 plus 4x. So because we can represent y that way, we get 2 pi square root 1 plus 4x. And now the ds that we use, since there's two types, so let's note, right? Two types of ds. ds is the square root of 1 plus dy dx squared dx, or we can use ds is the square root of 1 plus dx dy squared dy. But in this case, because we have a function here of x, we're going to use the one that ends in dx. So this becomes square root 1 plus dy dx squared dx. Now that's good because of the fact that we're going to need to find this dy dx, and we already have a y as a function of x, so we're on our way. So our surface area is going to be the integral of 2 pi square root 1 plus 4x square root 1 plus dy dx squared, that ends in dx. And don't forget, this is going to be over the interval from 1 to 5, because this is what was given to us. So we're going to go from 1 to 5 here. X is 1 to x is 5, as we looked at in that picture. And here's how you set this up. Okay, don't start to look at this and say, I want to rotate about a different axis just because. You're first learning how to go about these examples, and you have to learn how to do it right first before you start looking at all the permutations. So this is how this will work. And I should remark, this is what we need to determine. And we already know what y is. Y is the square root of 1 plus 4x. So since y equals 1 plus 4x to the 1/2, dy dx is 1/2, 1 plus 4x to the minus 1/2, and then by chain rule, we differentiate, and this is 4. So altogether, we get 2 over square root 1 plus 4x. That's for dy dx. Now, squaring this gives us 4 over 1 plus 4x. Now, don't forget what we have to do now is we have to add 1 to this term. So 1 plus 4 over 1 plus 4x. And then so our 1 now we can write as, we can replace that 1, remember, with something like 1 plus 4x over 1 plus 4x. We can be consistent. Let's just keep that same color. So I'm going to say here's 1. replace this with 1 plus 4x over 1 plus 4x plus 4 over 1 plus 4x. And we end up with, looks like it's 5 plus 4x. And this is 1 plus y prime squared, where that's dy dx. Now don't forget, you say, don't we need the radical? And we do. We have the radical with this now. So let's remember what that surface area formula was. Integrate from 1 to 5, 2 pi, square root, 1 plus 4x, 5 plus 4x over 1 plus 4x dx. So doing a little bit of algebra now and pulling out my constant, it looks like I have 1 plus 4x, square root of 5 plus 4x here, 1 plus 4x dx, and ladies and gentlemen, we get some cancellation. 2 pi, 1 to 5, square root of 5 plus 4x dx. So here's how we actually, go about the surface area question. And now I'm going to say this is a nice u substitution integral, where u is 5 plus 4x. Okay, so if that's the case, then you guys know that what is du? Right, du dx is going to be 4, or dx is du over 4. So when I do u substitution now, this is 2 pi integral square root of u du over 4. Now let's think of the limits here. Okay, because u is 5 plus 4x, if I plug in 1 for x, the lower limit, right, becomes 9. The upper limit, when x is 5, we get 25 for the upper limit. Remember, we're going to plug these values in here. X is 1, x is 5. So here's how we get our limits now. So it looks like it's going to be pi over 2 integral from 9 to 25 u to the 1/2 du. And I guess we get what? Pi over 2 u to the 3/2 over 3/2, which is pi over 2 times 2/3 u to the 3/2. U is 9 and 25. Pi over 6 u to the 3/2 from 9 to 25. Okay, double check to see if we're okay with that. All right, 1/2 plus 1 is 3/2, so we get 2/3. Yeah, it looks like we get cancellation here, right? You guys okay with that? Double check. Anyway, pi over 6, 25 to the 3/2 minus pi over 6, 9 to the 3/2. Factor pi over 6 out. Use the definition of 25 to the 3/2. Definition of 9 to the 3/2. 25 times 5, 9 times 3. So we get pi over 6 times 125 minus 27. 98 pi over 6, it looks like. Now 2 goes into 98 49 times. 49 over 3. 9, 10, 11, 12, 13. It looks like we get 49 over 3 pi. Anyway, double check this one. And let's write a nicer 49, but you guys see that's a 49. Okay. Now let's go back and look at this curve here, because what sometimes happens is students will say, well, I don't want to rotate this about the x-axis. I want to try to rotate this about the y-axis. Well, what will happen now if I rotate this about the y-axis, right? So let's kind of see if we can write on this. I'm not saying you do this, but that's a common question. And they said from 1 to, which is right here, to 5 again, right in the middle. Here's the curve. And you rotate now about the y-axis here. What that does, if you rotate about the y-axis, is your curve that you're rotating looks somewhat like this. Not completely, it's not so symmetric. But that radius that you have now will be something that looks somewhat like this here, because you're going to create a solid here. We don't have the rest of the curve. So it looks like it's 2 here. Who knows? Something like that. In this case, the radius will be a value of x. So here, r equals x. And so if you said, oh, 2 pi r ds, now in this case, you replace that just with an x. And the ds, since they gave you here, y is a function of x. Right? They gave us this. You're going to still need the ds that ends in dx. So we still need 1 plus y prime squared dx, where y prime is dy dx. But you're going to leave your radius here. Here's the point. You leave this radius value just as the x variable. You leave it alone. And that's what you'll use. That's not what you have, but that's what you use. And then that gives you an integral that may not be, by the way, integrable. But that's what I mean by be careful here, because the key is to find a radius value. And sometimes students simply just don't, they want to answer 20 questions with one question. And don't just say, I want to rotate it by a different axis. You can. What does it look like? You can. It looks like what I just showed you. But you now have an integral that may not be integrable, or you don't have a technique to integrate it. Okay? So I've remarked about this in lecture. But here's an example. Let me give you another example. We're going to rotate again still about the x-axis here. So we get y equals 16x cubed plus 1 over 2x and again rotate about the x-axis. So to show you that particular curve, 16x cubed, right? Let's get this here. 1 6 16x cubed plus 1 divided by 2x. And this is for x is 1/2 to x is 1 here. So if we get this curve out here, make that a bit bigger. X is 1/2 to x is 1. Okay, so 1/2. Let's see, how many of these do we have? 1, 2, 3, 4, 5. So it's like 2.5. Okay. All right. We're going to take that little strip and rotate that about the x-axis. And again, we get a radius value here. Remember, this is going to be our r, our circle. Doesn't look very good. But the radius value is again going to be, right, same value here, same length. That's the y value. So r is going to be y here. Our radius is y. Okay, that's good to know. Radius is y here. And sure enough, what do we notice? They give us what y actually is. So our radius is going to be now 1/6 x cubed plus 1/2x. So our radius is y. We're going to plug that in right here. Okay, you're going to replace this with a y value, and y is given. So what that means is our surface area is the integral 2 pi, now 1/6 x cubed plus 1/2x, right? We've determined that the radius is y, which equals the function that they gave us. So this is our y value. And since this involves the x term, the ds that we use now, because we have to write that ds here, the ds that we'll use is the one that involves dx, so that we have a consistent integral. Here's dx. But we need dy dx squared. Okay. So we got to get to work. Since we have y, which is right up here again, y equals r, same thing. dy dx becomes, let's use some operator notation. d dx, 1/6 x to the cube plus 1/2x. Right, pull out the constants. Use properties of derivatives. 3x squared, 1/2 x squared plus 1/2. And there's a problem here. We have a typo. There's a typo. This is not the answer. Let's go back here. See if you guys can find this. This is d. Let's pull out the what? It's 1/2 d dx of 1/x. That's not really x. So this derivative is negative, right, 1/x squared. There we go. Now everything's fine. So I have 1/2 x squared minus 1 over 2x squared. Okay, everything's fine now. So square this. 1/2 x squared minus 1 over 2x squared. One half x squared minus 1 over 2x squared. 1/2 x squared minus 1 over 2x squared. We get 1/4 x to the 4th minus 1/4 minus 1/4 plus 1 over 4 x to the 4th. 1/4 x to the 4th minus 1/2 plus 1/4 x to the 4th. Now this is very similar to something we already seen. You're going to see what happens with this, okay? This is dy dx squared, right? We just squared this. We need to add 1 now. So that 1 plus dy dx squared becomes 1 plus 1/4 x to the minus 1/4 plus 1/2 1/4 x to the 4th. And you get 1/4 x to the 4th plus 1/2 plus 1/4 x to the 4th. And now here's my point. Here's what I want to remind you guys. This term was obtained by squaring dy dx, which is right up here. Now, we've seen this a couple of times already. This is what I want to remark. You see this over and over again. What you're looking at is a perfect square trinomial. So if you factor, this is 1/2 x squared plus 1 over 2 x squared squared. Perfect square trinomial. So you can get a hint of that by looking at the prior terms. Okay, you know perfect square trinomial, right? Here it is, but there's a plus sign here. There was a negative sign. I'm sorry, there's a negative sign and a negative sign. The difference here is plus, addition. So that makes a lot of sense because we really need to find the square root of 1 plus dy dx squared, which is the square root of the term we just found, the perfect square trinomial. And this is the definition of absolute value. And since we're looking at the interval from 1/2 to 1, this term is always positive. So we get to remove the absolute value sign. So ladies and gentlemen, this is really all the algebra you have to do with this particular question. I wanted to show you guys how this works because if you go back and remember, all we found, which is what goes right in here, we still have this y, our radius value. We still integrate with that constant function, and we're going from 1/2 to 1. So we haven't integrated yet. We're just setting up that particular integral. So let's write it all together. Surface area, 1/2 to 1, 2 pi. X cubed over 6 minus 1 over 2x. And then we have x squared over 2 plus 1 over 2x squared. And then that'll be a dx. So at this point here, you're going to have to do a little bit more algebra. I'm going to say you're going to have to multiply here because we're going to have to integrate, right? So you're going to have to multiply, which really means use FOIL. So we integrate from 1/2 to 1. You can factor out the 2 pi. Now our first terms are going to be, if we multiply, looks like it's going to be 1/12 x to the 5th. Outer terms, if you want to do FOIL, outer terms now, looks like it's going to be plus 1/12 just x. So, okay, inner terms, minus 1/4 x. Okay, and then the last terms, minus 1/4 x cubed here, dx. Now, it's really easy to make a mistake, so let's just double check to see if everything's what it should be. Okay, and let's go back. I think I see something. Do I see anything here? Let's go look at the original curve they gave us. What's the curve they gave us here? 1, 6. Okay, x cubed plus 1 over 2x. Okay. Anyway, looks like we're good. Let's make sure this is, sorry, is that plus or minus? That looks like they gave us originally plus. Let's double check. Yeah, we look like we had an addition sign here. Okay, since we had an addition, we have addition. Let's make sure that's addition. All right, right in here. Here's my point. Okay, so that's a plus. It's all plus. All right. I would combine some terms here, right? I would say multiply the top by 3, bottom by 3. So I'll have 2 pi, we integrate from 1/2 to 1, 1/12 x to the 5th. 4/12. This is going to be really 1/3 x. Double check the arithmetic. And this is plus again. Plus 1 over 4 x cubed. Okay, 1/12 x to the 5th plus 1/3 x plus 1/4. Okay. Now, I guess I'll remark here, you're going to need to integrate. So what you should get when you integrate here, I mean, if you like, you could write it all this way. Use properties of integrals. Maybe that's going to be better for us. Yeah, just use properties of integrals here. 2 pi, 1 over 12 now. This is x to the 6 over 6 plus 1/3 x squared over 2 plus 1/4 x to the minus 2 over minus 2. And this is from 1/2 to 1. Looks like it's 1 over 72 x to the 6 plus 1/6 x squared minus 1/8, and the x squared is in the denominator here. You go to 1/2 to 1. So I'm going to have you guys check your arithmetic. My final answer is 263 over 256 pi. Okay. There is another example for us. All right. We're still rotating about the x-axis here. So on a remark, we're still going to rotate. About the x-axis. We're still on the x-axis. So now I'm going to give you another function. X here is 1 plus 2y squared. And remember, y goes from 1 to 2. Okay? Now let's go to our graph, because remember, if we say our surface area is an integral of 2 pi r ds, we want to always know first what is r equal to. It's either going to be y or it's going to be x. Let's look at the curve here. Okay. X now equals 1 plus 2y to the second power. And they want to look at this from 1 to 2. So, okay, let's see if we can figure something out. Okay, so we're rotating. Let's get our from 1 to 2. We're going to rotate here about the x-axis. Y goes now from 1 to 2. And I think we're going to have to delete that. Make this smaller here. Okay, that might be a little better. Yeah, that's a better picture. Here's y from 1 to 2. And we're going to take this portion of the curve and we're going to rotate this about the x-axis still. So if I said to you guys, this is a nice picture. If I can, my blood sugar. We're rotating this curve about the x-axis. I can say to you guys, here's my radius. Now, the radius value looks like it's going to be what? What's the radius here going to be? Is that going to be an x value or is that going to be a y value? Right? This radius here, this distance, is a vertical distance. So that means my radius is a y value. Okay? It's a vertical distance. So that's a corresponding y value right out here. Okay? Because we're rotating about the x-axis. So if we rotate it about the y-axis, the radius is going to be an x value. But here my radius is a y value. Vertical distance. Okay. So we know the radius here is a y value. So let's put this together here. The surface area is 2 pi y. We have a ds. Now if I go back, I'm going to notice, but I don't have, you know, I have y. I don't have, I have this x as a function of y here. So x equals gy. And I'm not going to solve this. I'm going to say to you guys, don't solve this for y. Just keep your radius here as a y value. Okay? That's fine. And notice my limits are from y is 1 to 2. So I'm already set here where you have y equals 1 to y is 2. I just have to use the ds that ends with dy. So let's get our computer back. So we need the ds that ends with dy. And you say, well, which one is that one? Well, square root 1 plus, remember, if it ends in dy, it changes here. This is going to be dx dy squared. And that's good because we have x as a function of y. That was given. So we're going to use this to be consistent here with our dy and our y variable. So all together now, let's see what that surface area formula kind of looks like. 1 to 2, 2 pi y, leave it as that, square root 1 plus dx dy squared dy. We now have to find what goes in this radical here, right? We got to find what goes in that particular radical. So I'm glad we have x is going to be 1 plus 2y squared, which means dx dy becomes d dy of 1 plus 2y squared. Dx dy becomes 4y. So if I square this, we get 16y squared. And you say, okay, let me add 1 to this dx dy squared. I get 1 plus 16y squared. And you say, but we really need the square root. So altogether, here we go. This is what we need to find. So let's remember here, our surface area formula is, in terms of y, 2 pi y times that radical. And that means y goes from 1 to 2. Okay, a very nice and simple integral. We're going to use u sub, because if you see what's under this radical, we got 1 plus 16y squared, and this is just a y here, so that's pretty good. So let's use u sub here, where u becomes 1 plus 16y squared, and then du dy. 32y. So that dy is du over 32y. So this integral now, using u sub, let's do it this way here. 2 pi y square root of u du over 32y. And let's look at our limits. Okay, because I know, for example, the y's will go away. We're going to get pi over 16, the integral of u to the 1/2 du, but we said, what about the limits now? So go back here, remember our limits. This is y is 1, y is 2. However, if I plug in 1, I plug in 2. For the lower limit, y is 1. Looks like we're going to get 17 for u. And if I plug in 2, 2 squared is 4. 4 times 16 is 64, plus 1 is 65. So we plugged in the values of y to get our new limit values. All right. And we actually simplified here, so you guys know 2 and that 32. So you end up with pi over 16 now. U to the 3/2 over 3/2 from 17 to 65. And this is pi over 16 times 2/3, u to the 3/2, 17 and 65. This gives you pi over 24. U to the 3 halves, 17 to 65. So, yeah, 2 and 16 cancels. That's 8. That's a 24. Anyway, pi over 24, 65 to the 3 halves minus that pi over 24, 17 to the 3 halves. It's going to write a better 24 here. And factor out your pi over 24. 65 to the 3 halves minus 17 to the 3 halves. And what that looks like, so you guys know, use the definition. This is going to be 65 times the square root of 65 minus 17 times the square root of 17. And we're done. So this is revolving about the x-axis. So, I mean, we could look at also a few here. Let's revolve about the y-axis. And so I'm going to give you guys a few examples that look like that. I get y equals 1 minus x squared over the interval from 0 to 1. That was given to us. They want us to revolve this about the y-axis now. In case you guys didn't know, that's a parabola that opens down. But anyway, let's take a look at that curve. One minus x to the second power here. And let's see if we can remember here what's going on here. So we take this curve, take more screenshot. Right, we want to be able to write on this. Okay, so remember, we're going to rotate about the y-axis. So here we go. Sorry, rotate about the y-axis. Now I go from x here is 0 to 1. So they're talking this. Let's see if I can get there. So they're going to take this portion from x is 0 to 1. Right? Remember, the key idea is, so what is our radius here? Well, we're going to revolve this about the y-axis. This is nice because we then get this kind of shape here. And as you guys can see, my blood sugar level is low, which is actually good for a diabetic. That's why you see these funny lines the way I do it. And what's our radius now? Here's the radius value. Now, since this is horizontal, this radius value, this distance, is the same as this distance. It's horizontal. So in this case, it's an x value. So our radius value is x here. That's the idea. It's horizontal. It's the same. So whatever that r value is, this is the corresponding x value. Our radius is x. This is a kind of nice picture. And in that case, our radius is x. So remember this. Surface area, integral 2 pi r ds. Our radius is x. So we're going to plug in for this radius an x. Now, be careful here. You say, okay, if my radius is x, because we've seen the geometry of the picture, but what did the author give us? They give us y is 1 minus x squared over an interval in terms of x. Don't be tempted to solve for x and do it that way. Just be grateful. You could leave your radius just as x. What that means, though, you need the ds, right? This portion has to be the one that ends in dx so that you're consistent and you can integrate, meaning you have to have the same variables. So that is 1 plus dy dx squared. And that's nice because y here is a function of x. We can find dy dx. So everything is set up nicely for us. Let's just clean this up. 0, 1, 2 pi x, square root 1 plus dy dx squared. And there's a dx. So we need to differentiate y with respect to x, since y equals 1 minus x squared. Y prime is minus 2x. Now you can say, can I write y prime or can I write dy dx? It does not matter. I actually prefer y prime personally. Let me show you why. Y prime squared is negative 2x squared, or we can say y prime squared is 4x squared. 1 plus y prime squared is 1 plus 4x squared, but we simply need the square root of that. So we have square root 1 plus 4x squared. So all together now, let's take a look at this. We just found what we needed right up here, but we already have 2 pi x. Surface area is an integral 2 pi x square root 1 plus 4x squared dx, and x here goes from 0 to 1. And so as you guys can see, this is another nice u substitution question here, right? 1 plus 4x squared is going to be your u. So when u is 1 plus 4x squared, du dx is 8x, or dx is du over 8x. So let's plug this in, right? We got the integral 2 pi x square root of u du over that 8x, and we get some nice cancellation. So we end up with an integral. Let's pull out the constant. It looks like it's pi over 4, right? That's u to the 1/2 du. So let's double check. The only thing is we need our limits, and we know u here, or we should say the interval is from 0 to 1, so u here is 1 plus 4x squared. I got to plug in a 0, and I got to plug in 1 here for x to get my lower and upper bounds. So when x is 0, u is 1, and when x is 1, u is 5. So this is what we use to get the limit values now. All right. Pi over 4 u to the 3/2 over 3/2. Evaluate this from 1 to 5. And I get pi over 4 times 2/3 u to the 3/2 from 1 to 5. So it looks like I end up with pi over 6 because I can simplify here, right? 2 and 4, yeah. U to the 3/2, 1 to 5. So pi over 6, 5 to the 3/2 minus pi over 6, 1 to the 3/2. Factor out your pi over 6. You get 5 to the 3/2 minus 1 pi over 6. The definition of 5 to the 3/2 is what you see here. So here we go, ladies and gentlemen. And there it is. So this is an example where we rotate about the y-axis, and as you guys can see, everything kind of fits very nice here. Okay, we're keeping it simple. Right, here's all the work here for this particular rotation about the y-axis. All right, now let's look at one more. Y equals 1/4 x squared minus natural log x. X goes from 1 to 2. Remember, we're going to rotate still about the y-axis. Okay, so remember our surface area formula. 2 pi r ds. What is r? Here's what we're looking for, the r value. So if we go to our curve here, one-fourth x squared, so 1 divided by 4, let's get out of there. 1/4 x squared minus 1/2 natural log x. So we need another function. Go to functions, and there we go. Okay. Now x goes from, in this example, 1 to 2. So I guess we could look at something like that here. Let's do it all the way here. Okay. So in this example, x goes from 1 to 2. So we have, this is x is 1. This is x is 2. We're going to take that strip and we're going to rotate about the y-axis. And if you take that strip, ladies and gentlemen, rotate about the y-axis, I'm going to say here at -1, I guess you're here, all the way at -2. Where are you at? Maybe something here. This strip is on the other side. So if I take, let's change the color here. I didn't mean to do that. Let's just change the color. Okay. I want to find the radius value. And as you guys can see, my radius will be, if I do it this way, sorry. Let's look at it this way. This will be my radius value, right? Oops. Nope, 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 nope. My radius value is like here, kind of that distance there. So here's my r. So you have to ask yourself, is that r a horizontal or vertical form of distance? Well, that looks horizontal to me for the r. So that's an x value. R here is x. It's my radius. So we keep it simple. R is x. That's what we get when we rotate about the y-axis. R is x here. So I know r is x. Replace this with an x. My surface area is x is 1 to 2. 2 pi x ds. So if I go back and look at what I'm given, I'm not given x, I'm given y. That's actually a good thing. That's a very good thing. That makes things nice and easier because that means my ds is going to be the square root, and then it has to end in x so I can be consistent with my integration. These variables here have to be the same. I just have to find 1 plus dy dx squared, and that's good because y here is a function of x, so that's going to be a lot easier to do. So let's do that. dy dx. I'm going to use operator notation. 1/4 x squared minus natural log x. This is going to be, I'll do it this way, 2/4 x minus 1 over x, right? Which is 1/2 x minus 1 over x. And let's double check here. I think there's a mistake. Yeah, I think there's a constant. I apologize to you guys. The original question had actually minus 1/2. Okay, and that's going to be important for us. That didn't change the graph much, by the way. But anyway, it's going to change this derivative here. So I'm going to go back here. Apologize for that. So I want to remind you, this is going to be a 2. You'll see why this needs to be the case. Anyway, so these problems are specially chosen, ladies and gentlemen. They're very, very specially chosen. So this is my derivative. This is at y prime that we're talking about, right? Okay. As you guys can maybe suspect, what you've seen in the past is this symmetry, because we have to square this, right? 1/2 x minus 1 over 2x squared. So you might get a little suspicious of what's going on and why that had to be a 1/2. We needed this nice symmetry, ladies and gentlemen. Specially chosen question. So put that constant back in, right? Now, we multiply again, which really means use FOIL. And we'll get 1/4 x squared, outer term, minus 1/4 inner term, minus 1/4 plus 1 over 4 x squared. And you end up with 1/4 x squared minus 1/2 plus 1 over 4 x squared. Okay, don't forget, we have to add 1 to this. And you end up with 1/4 x squared, now plus that 1/2. There you guys go. You see where we're going with this. It went from minus to plus, a perfect square trinomial factor. So we must have seen this about 5 or 6 times. Okay, factor, perfect square trinomial. That was 1/2 x squared. Now it's plus 1 over 2x, ladies and gentlemen, and that's squared. This was that 1 plus y prime squared. So this is why you really had to have that 1/2 to begin with right here. This is why we had to put it in. Sorry about that. This is the original curve, but nevertheless, that constant didn't change much of anything. And you want the square root of that. Now remember, these are for values of x that are between 1 and 2. And that gives you the following. 1/2 x squared plus 1 over 2x. That's positive. Okay. This is going to go right up in here. So here's your integral. 2 pi x 1/2 x squared plus 1 over 2x dx. And that goes from 1 to 2. Okay, and so in order to integrate, it's very simple. Just distribute. And in fact, if you want, you can keep the constant. I don't know. You can bring it out maybe. But you can actually use the 2 pi if you wanted to integrate. That's fine. So this is still going to be, how about if we do something? Yeah, let's keep it out. Sorry. So that's 1/2 x cubed plus 1/2 double check because the x's will cancel, right? And factor out a 1/2. So this is actually going to be pi integral. Looks like it's x cubed plus 1 dx. And x is going to be from 1 to 2. So I'm just going to double check my algebra here to make sure that I'm okay. Okay. Is that x cubed or x squared? That's x cubed, right? So let's just double check everything's fine here. I think, up. Here we go. Yeah. No, this is just an x, looks like. There we go. That's just an x. That's just an x. Yeah, there we go. That's just an x. That's where it is. Okay, so that makes this a nice x squared. And we can factor it out. So we get a nice, at the end, what do we have? X squared there, okay? So it looks like we can factor out the 1/2. So we just have pi. Yeah, it looks like we're good now. All right, you guys okay with that? Just make sure we're okay. All right. So working on a nice Sunday. How fun is that? 1/3 x cubed plus x. Evaluate that from x is 1 to 2. So we get pi. One-third 2 cubed plus 2 minus pi 1/3 1 cubed plus 1. We get pi 8/3 plus 2 minus pi 1/3 plus 1. And actually we can factor out pi and say we get 8/3 plus 2 minus 1/3 minus 1. Doing some algebra, factoring pi out, distributing. So I get pi here, and this is actually 7/3 now plus 1. And then 1 rewrite as 3/3. So we get 10/3. So this is 10 pi over 3. And let's do a nice box. So we get 10 pi over 3. Anyway, here's some nice examples for you guys. I said I'd get them for you on a nice Sunday here. I'm going to upload them and announce them that they're there. So I hope you guys enjoyed these examples and the process of finding surface area. Not too hard. Just stick with what they give you and don't complicate your life. There's going to be some arithmetic, though, and a little bit of algebra. Okay. Have a great rest of the day, and I'll see you guys tomorrow, or hear you guys tomorrow.